Hi, I'm Casey Matsubara, and welcome to the second talk about quantum gravity and the nature of space and time. And as I mentioned in the end of the last talk, this one will address two different things that are quite different from each other and not very related. So if you're only interested in one of them, you might look only at that one. I'm just telling you about that. So the first one was talking about string theory and space-time and dualities in string theory. And the second one is to mention a little bit about the problem of time in quantum gravity. So let's first start with string theory and dualities. As mentioned in the previous talk, there are these extra dimensions in string theory that are often thought of as being spatiotemporal, and sometimes they are, but it becomes a little bit more subtle how to think about these things in the presence of dualities. So what is a duality? Be warned though first that the term or the word duality is used in many different ways in mathematics and physics. So the way I describe it here may not fit absolutely all uses of the term, but I think the way I describe it is relevant for the kind of dualities we're discussing in string theory. So it's basically you have theoretical descriptions that are physically equivalent, and as part of that means that everything potentially measurable will be the same. On the other hand, they seem to, at least the more interesting or weird ones, seem to give very different pictures of reality. And the question is, how should we think about these situations? And for a philosopher or a philosopher of science, it might be quite tempting to think of these in terms of cases of underdetermination of theory by data, because these would be empirically equivalent theories, even though they describe different worlds. And even though I will not completely rule out that reading of dualities, and if one really insists, one can try to spell out such an account. But I would say the standard view among physicists, and also I would say among most philosophers that have looked at these issues, tend to think of dualities instead as describing the same reality, and hence not being competition. Note though that this is something that if you want to and go into this field, try to challenge and discuss and try to kind of answer and defend some other view that they perhaps are under determination or not. I will not go into that. Instead, I will kind of explore the consequences, the conceptual consequences of adopting the most popular view towards these kind of dualities, namely that they describe the same reality. And if they do, then we cannot take all things that they seem to say at face value. We have to kind of base our physical representation on the shared part of these pictures, things that are not in direct conflict in one picture from another. And space-time, if understood to be something physical, must also be based on this kind of shared common core or common structure that is identified under the dualities. So we have to kind of build it up from that basis. And string theory dualities, in string theory, dualities can connect very different backgrounds. For instance, the suggested, the prima facie space-time might have very different shapes or size. And things like that. And if we take these at face value, we kind of become completely confused if we try to think of this as representing the same physical situation, how to make sense of that, and that is then very challenging. We will be, because the prima facie pictures are in conflict, we must be very wary of trusting them as correctly representing space-time. And that is why I, in the previous talk, had all these kind of subtle warnings that maybe not so subtle warnings about the way that the extra dimensions, think of them as spatiotemporal, might be complicated due to these dualities. So the simplest case is T duality, where one dimension or more is compactified to form a little circle. And typically these are supposed to be very, very small, kind of close to the quantum level, and we will not actually observe them. But the weird thing is that a very small and a very large circle turn out to be dual and physically equivalent. And then it's difficult then, what is the radius of spacetime? We have like one picture that says it's super small and another that says it's super big. In T-duality, it turns out that when one looks more kind of carefully at this situation and trying to figure out how this would actually appear phenomenally or effectively, or how we kind of would actually measure things in such a situation, it turns out that even though we kind of mathematically start with, regardless of whether we mathematically start with the small one or the large one, it turns out to effectively look like the larger of these diameters. And this shouldn't really be seen as saying that, oh, the large one was right all along. That is not quite the lesson to bring home here. It's rather that you have two pictures, and then to trying to figure out what the effective or shared part that both pictures have in common, what that is kind of the important thing. And that is what we should think of as spacetime. While the other kind of initial radii should be perhaps thought as kind of a mathematical stepping stone to get there. And to really understand that, you have to kind of think more carefully about the transition from the classical description to the quantum description of this situation. But that's not something I can go into in any depth here. There are also other dualities where the shape or topology of the extra dimensions are different from one to another. You've probably heard about topology in a situation where it's basically you're allowed to stretch things, but the number of holes and how they are connected and all that might not change. So a typical example to describe topology differences is like a sphere is topologically different from a donut shape. We cannot twist a sphere into a donut without cutting it up in some way, and vice versa. So they have different topology. And in some of these dualities, the extra dimensions have a different topology. And then it becomes even more difficult to figure out what is kind of the relevant shared physical description of spacetime. And then it becomes more difficult to think of all these extra dimensions as spatiotemporal. Maybe in some situations you can think of them as that, but if both are very small and both are compactified at these kind of micro level, there is no kind of clear spatiotemporal picture that arises for these extra dimensions. On the other hand, the bigger dimensions that are the same in both pictures, they warrant such an spatiotemporal interpretation. It makes sense to think of them as spatiotemporal. And to really understand that, one has to understand how, at the deeper level, the quantum string theory consists of the strings kind of form sheets, two-dimensional world sheets. And somehow the quantum description of this two-dimensional quantum field theory on the surface of the string somehow is more fundamental, and it's actually that one we should trust more deeply. So if we try to figure out something genuinely physical and not something that is just an artifact of one dual description from another, presumably we have to go deeper and kind of base our picture on this kind of common results, the common quantum description that turns out in both dual pictures. And I understand this might be quite difficult to follow what that is and what we mean by that without some background. But the main point is that we cannot trust naively one picture or the other. The main point is just we have to try to figure out something that is based on this shared physical content. There is also other dualities known as ADS-CFT or gauge gravity dualities. And the weird and interesting thing with this is that they combine, in one side you have a more quantum field theory, particle physics description, and on the other side you have a string theory description. And they also have very different dimensions in the background that we would at least naively identify as space-time. And it might turn out that these dualities are not exact. They might be approximate, and then there might be a different story to be told. But if it turns out that these are absolutely exact, and that the way of thinking that I've talked about now before, that everything physical must be based on the shared structure, this kind of complicates this way of naively identify any of the sides as being space-time. The space-time, if we think of that as something physical, must be based on the common core. And given that this kind of just gives a more dramatic example that the prima facie picture suggests very different dimensions of this that one would naively identify as space-time. And some people and some physicists have thought of that because one description has a fewer number of dimensions than the other, that one can here think of this as space-time of a higher dimensionality emerging from a theory of lower dimensionality. But if the duality is completely exact, that picture kind of doesn't really make sense. There might be, if it's an approximate duality, it might be possible to think of emergence in some sense here. It might also be possible of thinking of emergence in this case in terms of different solutions having different kind of effective or relevant physical spacetimes in different parts of the full space of physical solutions. But that is kind of a more subtle description than just saying that the duality is from the lower to the higher dimensional one. Because phrasing it like that seems to put one of them to be more fundamental than the other. And that doesn't work if duality is supposed to be a symmetric relation. But still, I mean, there might be other more kind of careful and subtle ways one can think about emergence even in these cases. But the kind of simplistic just from the lower dimensional to the higher one is kind of probably not the right way to go. So that kind of concludes my first topic, which is about space-time and dualities in string theory. And of course, there are a lot more to be said about these issues. It's still debated by many people. And as I mentioned in the beginning, the view where dualities are instead thought of in terms of underdetermination is perhaps completely not ruled out, and it's still debated. So that might be something you find interesting to kind of look more on at and perhaps contribute in one way or another. I will now instead switch to a completely different topic and a completely different issue that also arises in quantum gravity. And that is the so-called problem of time. And that appears most kind of, let's say, primarily or most apparently in a number of approaches to quantum gravity, such as loop quantum gravity, the so-called canonical approaches. I'm not saying that some kind of counterpart or some version of the problem of time doesn't arise in other approaches, such as string theory, but it's not kind of as explicit or clear how to think about it there compared to the canonical case that loop quantum gravity is a case of. And in canonical cases of quantum gravity, one part is that one kind of needs to divide space and time, divide space-time up into space and time again, in a perhaps kind of artificial way. At a classical level, we can kind of slice through space-time and kind of fix a moment of time in different ways, and then try to kind of, based on initial condition, trying to figure out how that develops and kind of form a space-time from that. And if this works out, we can choose very different kind of slicings, and they will end up with effectively the same results, up to some subtleties that I will kind of not go into. But in that sense, we can kind of generate a four-dimensional space-time from a three-dimensional space, and think of it roughly in terms of how that three-dimensional space develops through time. When one attempts to quantize the theory, it becomes weird. And the formalism seem to suggest that what we would expect to be something that develops or changes is just the same. And the relevant time parameter kind of falls out and doesn't seem to play any role at all. of course, this is difficult to explain in any kind of fully meaningful way at this kind of popular description, but it's roughly to say that it seems to be that somehow time just doesn't play a role at quantum gravity in the quantum gravity description here. And people have responded very differently to this, and one needs to find out, like, how can such a formalism work, and how can we kind of figure out how our experience of time can be derived from such a picture. And some of these responses challenges the way space and time are combined into space-time. Because one of the most interesting and kind of central parts of relativity theory was the way space and time was combined into this totality, space-time, where there was no objective simultaneity that is kind of observer dependent and all, and many other effects. And we also know a lot of things about how the duration or the measured time will be dependent on how people move throughout space-time. So two people can age that, or the same age can kind of move very differently through space-time and end up being of different age once they meet again. And since we know that, any kind of approach need to kind of be able to explain how these results can be fit into the new picture, so to say. I will now just briefly present three different responses, and the first two, I would say, are more kind of challenging the lesson learned from relativity more than the last one. And one of them is Barbour's response, Julian Barbour. And that's kind of very strange and interesting idea that what really exists is just a number of three-dimensional nows, three-dimensional like moments of time, and they are not connected to form a space-time. So they are just individual nows there, but some of them are so-called time capsules. They are the ones that indicate some kind of a history, and in that you have brains with memories of a past in that fixed now. You have books and recordings of things that presumably happened in the past, etc. And other events, for instance, you can have a dent in a car that indicate that there must have been some kind of collision there. But we only have a large collection of these nows, and they do not form this kind of an actual space-time. It's just some kind of a quantum collection of these events that somehow give the illusion of time, the illusion of change, when in reality, if Barbour is correct, there is only these kind of collection of individual three-dimensional nows. And time doesn't really play any role at fundamental level. That's kind of more of an illusion that appears from the collection of these nows. So for the philosopher, the more kind of historically oriented philosophers, there might be some kind of Parmenidean flavor here, that there is no kind of real change or something. But that, of course, is a bit of a stretch, but could be fun to mention at least. So that's just one response to the problem of time. A completely different suggestion has been given by Lee Smolin. And he instead believes that time is really objective. And space might be emergent in some sense, but space is really there. So given this kind of view of thinking about space-time, there is kind of an objective now. And the way he expresses it is basically along presentist lines of space-time, using kind of the more metaphysical discussion on time. Smolin's account would be presentist. And of course, there are many questions to ask about this. Does it even make sense to make these distinctions about presentism or not? But according to Smolin, it does, and there is kind of a way of thinking about space-time that is presentists, but still respect all these kind of empirical results we know from general relativity, so that even though there is an objective now, there is an objective concept of simultaneity. The way people age differently along different ways throughout spacetime, that is something that, of course, must be preserved, because that's something we can measure and know that is correct. So in this situation, it's almost the opposite way to Barbour. Here, Smolin is thinking of time as really real, and space might be more emergent, and in Barbour, it's kind of the other way around. And Carlo Rovelli and others as well, I think would not like to abandon this kind of general idea where space and time are kind of connected into space-time and are treated on par. So instead, they want to kind of keep that lesson. Rovelli himself kind of basically says that he thinks that the lesson from relativity that simultaneity, there is no objective simultaneity, is something that will not change, and that is a lesson that we will kind of keep. So instead, here, it's kind of more or less that both space and time are supposed to be emergent in the same way from this underlying quantum gravity in some sense. And it's okay, you say we have no objective time, but from this point of view, it's like, well, we shouldn't be that surprised about that, because that was a lesson we already learned from relativity and general relativity. We can choose different kind of ways of parametrizing. We can choose different relevant time coordinates and so on, but there is no kind of objective general time that goes for everyone. So instead of to actually make measurements and understand how we get results and how things change is to kind of find the relevant observables and find their correlations in a useful way. And of course, there are a lot of tricky things and issues to deal with here, but if one could figure out the relevant kind of observables and how they are correlated to each other, and you would be able to explain how time and space emerges from this kind of deeper quantum picture in a nice way. So this was basically just three ideas and three different ways of thinking of space and time. And I have here not really argued for one or another, other just shown how very different responses different researchers have ended up with. And that kind of concludes my short description of the problem of time in quantum gravity. And if you find that interesting, I encourage you to read more about it and try to think more about it. And now I'll just end with some final comments. That I hope that what I've talked about today is, of course, very basic and very introductory, but I hope to at least have given you some rough ideas of the ways in which quantum gravity may change our understanding of space and time. Another thing I would like to just throw in there is that some people have speculated that there might be some connection with development of the correct development of quantum gravity and how we should interpret quantum physics. Remember, I mentioned that how to interpret quantum physics is widely debated still, and there might be some connections here. It might be that the problems are not related and one can be solved independently of the other, but I think it's at least worth to keep in mind that there might be some connection. Another thing is that we now all have different kind of tentative, speculative approaches working to the same goal. Unfortunately now, sometimes people are very focused in one approach or the other. And one should also bear in mind it might be that different approaches have found different pieces of the puzzle. And the correct way ahead might actually be to kind of find different parts or different ideas from the different approaches and combine them in a new and novel way that is consistent and coherent and which we can test, etc. So for that reason, I think I would like to encourage people from the different kind of quantum gravity communities to communicate with each other, and also with philosophers. I think there is kind of a good idea to kind of be part of that, that we converse with each other on these issues, because it is very much still work in progress. And that was all I had to say. Thank you very much. But before leaving, I would also like to encourage you to look at the other videos and talks that we have on this website. And then you can learn more about various issues in quantum gravity, and I hope you will enjoy doing so. Thank you.